Hello, I'm Mr. Bob, and welcome to my Geometry Review video series. This video covers Chapter 12, Section 5, titled Symmetry. By the end of this video, you'll have reviewed recent lessons on identifying types of symmetry in figures, to include lines of symmetry and rotational symmetry. You will end with a review of a real-world problem to solve. If you'd like me to cover any of these topics in greater detail, please leave your request in the comment section below. Please subscribe to this channel if you find this video to be helpful. Thank you. Okay, let's start this review with a few definitions. So symmetry. A figure has symmetry if there is an isometry that maps the figure onto itself. Reflectional symmetry. If an isometry is a reflection of a plane figure, the figure has reflectional symmetry. Line symmetry. If a figure has reflectional symmetry, it also has line symmetry. Rotational symmetry. A figure that has rotational symmetry is its own image for some rotation of 180 degrees or less. Point symmetry. A figure that has point symmetry has 180-degree rotational symmetry. Objective 1. Identifying types of symmetry in figures. A figure has symmetry if there is an isometry that maps the figure onto itself. If an isometry is the reflection of a plane figure, the figure has reflectional symmetry or line symmetry. One half of the figure is the mirror image of the other half. Fold the figure along the line of symmetry and the halves match exactly. You can see that in the picture of this mask. There's a line down the, if you folded it in half, you can turn it, it's the same. It's exactly the same piece. If it was truly flat, you could flip the other one over and it would be exactly the same. The image on the Inuit sculpture at the right has reflectional symmetry about the vertical line down the middle of the face. It is possible for a figure to have more than one line of symmetry, but this one has one line of symmetry. Splits that face in the middle, and each half is exactly the opposite, the flip side of that. Example 1, identifying lines of symmetry. Draw all the lines of symmetry for a regular hexagon. So what does it say to do here? It says draw a regular hexagon. You've got the picture of it right here. Then draw the lines on the hexagon that make the mirror image congruent halves. And then how many of them are there? Well, it says here that there are 6 lines of symmetry. And what are those 6 lines? Well, the hexagon, we drew that out. But now what are the 6 lines? So this line here, oh, look at that crooked line there. My goodness, I can't draw straight at all. I have to like really. So this line right here, oh, I've still got the eraser on. Let's see, there we go. So this line right here carried entirely through the hexagon. There's one line, right? So there's a line. This is a line, right? If you cut this piece here down the middle with this first line, this section here to that point there would be the exact mirror image of this section on this side, right? We see that? Because it would get split right down the middle, right? That's what they're talking about. Well, you can do the same thing on on this is in the middle of the line. This is the same, cuts it in half. This one's the same. When you cut it through here, then these pieces here would fold across and be exactly cutting it right, mirror imaged. Same here, and same here. So how many are there? There's this one, this one, this one. So 1, 2, I'm going to change the color. There's 1, 2, 3, 4, 5, and 6. We didn't do the other side because it's the same line. This is the same line, so we can't count it twice. So there are 6 lines of symmetry in a hexagon. You can fold this hexagon along any one of those lines, and as you flip the paper over back and forth, it'll be the same image, only the mirror image of itself. Okay, example 1, check your understanding. It says draw a rectangle and all of its lines of symmetry. So why don't you go ahead and do that? When you come back, we'll talk about it. Okay, I'm assuming you paused the video and you thought about it and you now have your pictures drawn. So, and we're back ready to start. So I'm going to draw a rectangle. It won't be great. You know, I don't draw very well. So here's a little rectangle. Doesn't matter what the size is. It just has to be a rectangle. So what are the lines of symmetry? Where can you cut this in half and make it both halves look the same? Well, I'm going to change colors. I'll change over to gold. You can draw a line through here if I can get it right. So this is a line of symmetry. If you fold along that line, if this is a piece of paper, then both pieces will be the same, just the mirror image of the other one. And then you can do the same thing right here. Oop, a little straighter, I would hope, than I'm drawing, but you get the picture. You can fold this box over on itself. You can't do this with a square, though, because then there are more lines of symmetry, right? If you had a square, I'm just going to try and draw a square. It's close, but you know it's not one. So here's a line of symmetry here. Of course, here's a line of symmetry, just like the rectangle. But then there's also a line of symmetry here, and then a line of symmetry this way, right? If it's a true square. So rectangle has two lines of symmetry. Example 2, identifying rotational symmetry. Judging from the appearance, tell whether each triangle has rotational symmetry. If so, give the angle of rotation. So looking at problem A, question A, it says, is that triangle, does it have rotational symmetry? Well, this is an equilateral triangle. So that means that all the sides are the same, right? Those are all congruent. And the angles also are congruent. They're all 60-degree angles. But if these angles are all the same, what's going to happen is, how can I rotate this? I can rotate about the center right here. I can rotate 120 degrees, as you see here, in this picture down here, 120 degrees, and you get the same picture back. And I rotate it again 120 degrees. This point up here on the first rotation would say end up maybe here, and then on the next rotation it would end up here, but it would still, I couldn't tell the difference in the triangle. Rotational symmetry, 120 degrees. Now for B, it's an isosceles triangle. So these two sides are equal. These two angles are equal. But this one is different. This angle up here is something else. I don't know what it is. This, you could tell there's the only symmetry about this triangle is if you rotate it, you have to go all the way around 360 degrees for that to have rotational symmetry, and that does not include, is not included. 360 degrees is not included in that theory. Oh, okay. So isosceles triangle does not have rotational symmetry. So, okay, example 2, check your understanding. So as you know, they want you to stop and try this on your own and think about it. Stop the video, and then when you're done, come back and we'll talk about it. But what are the questions? Judging from appearance, tell whether the figure at the right has rotational symmetry, and if so, give the angle of rotation. And then in B, it says, does the figure have point symmetry? Okay, so go ahead and stop it, and when you come back, we'll talk about it further. Okay, A, judging from appearance, does the figure have rotational symmetry? And if so, what's the angle? Well, if you look at this, the only thing that in order to rotate this, you have to rotate it about a point. And you have to rotate some angle distance that when you get done rotating it, it looks the same. Well, if I put a point right here, there's my center of my point, and I rotate this all the way around 180 degrees, this piece, right, sticking up here, is going to be down here. So the answer is going to be yes. It has rotational symmetry. It'll look exactly the same once you rotate it 180 degrees. So that's the angle, and the answer is yes. How about, does it have point symmetry? The angle there also is yes, it has point symmetry. If it has rotational symmetry at like 180 degrees, then it has point symmetry. Okay, example 3. It's a real world problem. Tell whether each object has rotational symmetry about a line or reflectional symmetry in a plane. Okay, or both possibly. So the first one's a ping pong paddle. If we look at it, it says, does it have rotational symmetry? Well, look, the way we look at it right now, I'm going to say no. Let's go on to reflectional symmetry. If we were to draw a line right here down the middle of this paddle, and it's obviously I'm not going to be very good at it, but if we draw the line right down the middle like this, we can stand it up on edge, so to speak, and we can say, yes, this generally has reflection symmetry. If you fold this in half, it would match itself exactly when you folded it in half. There's no other way you could do that. Just this particular way is probably the only way. Now, is it true? Well, there might be logos and stuff, but this paddle itself, assuming that everything is equal, yes, it does have rotational, excuse me, reflectional symmetry. Does it have rotational symmetry? That's one that I'm going to probably be hard to go with. Although the book says it has rotational symmetry, the only way I can see rotational symmetry is if you stand this up on end or you look into the handle. Let's say that. You look down into the handle, okay? And you have the paddle flat as you're looking down into the paddle. So what you're going to see on end is you're going to see this, the end of the paddle, and you'd see it like that, right? The paddle curves and goes around, but you're looking into this end. Well, if you rotate this 180 degrees, it'll look the same again. But that's basically the only way I can see how you'd get the symmetry. As for the cup, it has reflectional. So if you cut it right down a line that cut right down the middle of the handle, right? Come down the cup like this, cut it right in half, and you had the same cut down the other side. And then you could take and possibly, you could see that the two halves were identical. That's the only way I can see how you can get reflectional symmetry. But you'd have to be looking right down the line that cuts the handle right down the middle into the cup, and then you on each side it would be the same, yes, but in no other way would you get reflectional symmetry. You're certainly not going to get rotational because there's nothing you can turn on that cup that'll give you, without going 360 degrees, that you can get the cup to repeat its view, the image. Okay. Okay, example 3, check your understanding. This is the final slide in this review. Tell whether the umbrella has rotational symmetry or reflectional symmetry in a plane. Well, if you look at this umbrella, I'm not sure how many sections it has. It looks like it has 1, 2, 3, maybe 8 sections. It might have 8. I'm not sure. Looking at the top, I'm not sure how many sections this has. However, if you draw your line, I'm going to draw it in red, I guess, because I've got a lot of blue out there already. So if you draw your line down the middle of the handle, all right, then you could say, yes, there's reflectional because of this half on this side. If you folded it in half, would make this side, right? It'd be the same thing. So down here on this side, it would look exactly the same as it does. It's got a point here. It's got a point down here. It's got this point here, this point here. Okay. So that's the symmetry that we're talking about. And in terms of rotational symmetry, if you look at it from the top, looking down, what are you going to see? You're going to see the point in the top, and you're going to see, the umbrella. Not a very good drawing, but you get the picture. As you rotate it, you're going to be able to see the same image, and it'll look the same. If you get 1, 2, 3, I don't. I'm going to say that there's a hexagon. So if that's a hexagon, then you rotate it every 6 times 6 every 60 degrees, and you're going to get a repeat. Okay, so there you have it.